Okay, maybe we'll begin. Welcome, everybody. It's my real pleasure to introduce one of our own, Professor Noel Clark. Um, Noel got his PhD in 1970s, early 1970, I guess, at MIT. Uh, his PhD thesis was on inelastic light scattering, which a technique that he continues to use in his research. After MIT, he did a postdoc at Harvard and then stayed on there for as an assistant professor until 1977. We really benefited from Harvard being short-sighted and not wanting to grow. And in fact, uh, there, while Noel was there were many other distinguished soft matter physicists there that ended up leaving. And we were lucky enough that in 1977, Noel came here and started a group, condensed matter, soft condensed matter, liquid crystal group here in Colorado, and been here for 50 years. Over that 50-year career, he published, on an amazingly number of seminal papers. His total publication list is approaching 600. Just to give you some other statistics, this 600 papers have led to 40 patents and were part of 50 PhD students' theses. His age index is 100, and it's difficult really to find an area in soft matter, and particularly in liquid crystals, where Noel has not pioneered and really led to, very, opening up new fields, new materials, new phenomena. Um, this work has been recognized by many awards. Some of the notable ones are he's a member of National Academy of Science. He is a professor of distinction at CU, and he was awarded, shared with Bob Meyer, the Buckley Prize of APS, highest prize in condensed matter physics that APS awards. Another kind of a notable distinction, Noel, is that he's an experimentalist, but he's equally good theorist. So you'd be hard pressed to find a paper. Out of these 600 papers, a paper where there's just an experiment, it's just data left as a sort of an open, with a question. I mean, although there's always raises many questions, but there's always a story. There's always a theoretical picture. He doesn't publish his work until there's sort of detailed theoretical understanding. Not to be confused with formal theory, but really a great physical theoretical picture. And so it's really something special about Noel's work. There's a beautiful interplay between theory and experiments in all his papers. And, I've been on a personal note, I've been lucky enough to interact with him for 30 years. He's, in fact, I'm also grateful to Noel for hiring me 30 years ago. And, I learned enormous amount, particularly about liquid crystals and how to think about physics from Noel. And often, he has me up there as in theory, but often what I find is Noel usually does the experiments, 10 different probes, 10 different ways to triangulate and decipher what the liquid crystal phases are, what the phenomena is. He figures out the theory, and then he explains it to me, and then I kind of make it a little bit more formal and respectable. So it's really, Noel does all the work. And he was also a director for 25 years of the Mercek Center and SF Center. Anyway, without further ado, Noel, he's going to tell us about one of these exciting, very exciting discoveries of ferroelectric liquids that actually goes back to the original conception of liquid crystal, going back to Max Born, the great Max Born, 100 years ago. And so it's finally been discovered, and Noel was at the center of that discovery. So please join me in welcoming Noel. Now it's on.
Yeah, okay. So acknowledging the people that have been working on this. Start out with Dave Walba, who's here. Thanks for coming. So Dave and Ava made the molecules. So they're at the top of the list. So then we've been doing experimental physics with our postdocs and students. We have our senior citizens and our undergrads. So doing theory and atomistic simulation with Leo and Dmitry Bedrov at the University of Utah, and these are the beamline scientists at the synchrotrons. So these are the topics. I had trouble getting the introduction to be under an hour, so it may not be in this order, and I'm sort of kind of winging it here. So, all right. So in 2020, we published this paper on an experimental set of experiments on this molecule. Okay, so this is the first liquid crystal molecule that's been sort of definitively identified as being ferroelectric, ferroelectric nematic. Generally what we're talking about of molecules in this talk will be things like this rod-shaped organic molecules, not too big. Okay, so this molecule was reported in 2017 by Richard Mandel. So it's RM, Richard Mandel, the 734th molecule that he's made. So this is the molecule. I've sort of sketched in its dipole moments. So dipoles are going to be kind of a major theme in this talk. These are some other representations of this molecule: the space filling, the outer surface of the electrostatic potential, and the surface of the molecule. So this end is sort of negatively charged, this end is positively charged. And then kind of the stick model. So notable here is that in this NO2, for example, we have a nitrogen and oxygen. So this is a strongly dipolar bond. So we have a dipole moment here very close to the end of the molecule, pointing to the left, and then on this end we have similarly almost a strong dipole, also pointing to the left. Okay, so in this paper, the phase sequence for this molecule was reported as isotropic, and then it went to the nematic 1 phase, and then at 133 degrees, a second nematic phase. Okay, so there was, so the report was we have a new liquid crystal with 2 nematics. Okay, there was only supposed to be 1 nematic, but so they found 2 nematics. And so that attracted our interest. And so the nematic phase is sort of sketched here. The molecules, this is a liquid, 3D liquid, where you have the spontaneous ordering of the long axes of the molecules. So this phase has a director field. So it's a vector field that tells you at a given place which way the long axis is. Okay, so it's 3-dimensional kind of fluid description of the molecule. And in this phase, the arrows represent sort of the net molecular dipoles, and you see half are pointing to the left and half are pointing to the right. So this phase is not ferroelectric. So this nematic 1 is just the nematic phase. That is sort of the workhorse phase of like in liquid crystal display technology, for example. Okay, so the second nematic turned out to be the ferroelectric nematic, and you notice here that all the dipoles are pointing in one direction. So now the field, so this phase is described by like a double-headed vector field. This phase is described by a vector field, which tells you in space which direction this average long axis is, and the polarization density of the phase. Okay, so this transition has been in the literature, liquid crystal literature, for a long time, 120 years. So Peter Debye and Max Born in the 1910s wrote mean field models for that phase transition between the ordinary nematic and the ferroelectric nematic. They were trying to account for liquid crystal order in general. There was, a small population of liquid crystal molecules at that time, and so the proposal was that you have liquid crystal ordering because of ferroelectricity. And this model is sort of drawn from the Langevin-Curie-Weiss model for the paramagnetic to ferromagnetic transition, this mean field model. They basically sort of went in the same direction, exchanging electricity for magnetism, so to speak. A sidelight is that at this time, the solid state ferroelectricity wasn't discovered until 1920. So these papers are effectively a predictive, especially this one, sort of predictive of the finding of ferroelectricity in solids. And actually, this model is very applicable to solid state ferroelectrics. Okay, now let's see if we can get the video to work. See, I have to click on this. Is that right? Okay. So we're looking at the nematic to ferroelectric nematic phase transition. In a test cell, so the liquid crystal is in between glass plates spaced by like 10 microns. And we're looking in transmission between a cross polarizer and analyzer. So we'll look at it again. So as this, sorry. Maybe we can't look at it again. Yeah, here it goes. So you see these striations appear along the average orientation direction, which is the white arrow. They coarsen, they turn into a series of lines, and then these lines organize themselves, and now we're in the ferroelectric phase. And so I'll be interested in this region here where the lines have formed loops, okay? So here are the loops. Now we're applying an electric field on this this sample. The electric field is in the direction along this average molecular orientation. So let me just play it again. So we apply electric field pointing down, the inside of these domains reorients. And this one goes away. When we switch the electric field going up, then this domain goes back to the original orientation and the outside reorients. Okay, so this is evidence that that this lower temperature phase has a ferroelectric polarization that's coupling to the field, and that the sign of this polarization is opposite. So these two domains are domains of opposite ferroelectric polarization. Okay. So the polarization appeared spontaneously upon cooling into this phase and formed domains, and these domains could be manipulated with an electric field. So these are kind of the essential elements of ferroelectricity. Okay, so we measured the ferroelectric polarization. So basically, this is the average contribution to the polarization of an individual molecule divided by its molecular volume in the phase. And so we end up with 6.2 microcoulombs per centimeter squared as a saturation polarization. Okay, so we wanted to try to understand this value. We asked, suppose the molecules were all perfectly oriented, what would the polarization be? Okay, so you can calculate the molecular dipole using quantum chemistry. You can measure the volume of the molecular volume from the density. And so we can calculate the sort of maximum possible ferroelectric polarization. So that comes out to be 6.8 microcoulombs per centimeter squared. So we have kind of an incredible degree of orientational order in this phase for a liquid crystal. So we have this value, we have our measurement. Okay, so then we wanted to sort of understand this better, so we turn to atomistic simulation. Okay, so this is a simulation box with 384 of these molecules, periodic boundary conditions. So this simulation is started with all the molecules in the same all the dipoles in the same orientation, all the molecules in the same orientation. And during the simulation, they don't flip over. So we have 100% Ising order. There's a big barrier for end-to-end flips. So that's rare enough so that in what we have in terms of resource for the simulation, we never see that the flipping. So this is kind of well, we're not sure what. Okay, so we could calculate from the simulation. Then we can calculate the polarization in this condition when we have 100% Ising order. So we don't have perfect order because the molecules are sort of fluctuating around. Okay. So this so in the simulation we end up with a polarization 6.2 microcoulombs per centimeter squared. So the same as the experimental value. So we interpret this to mean that in the saturated ferroelectric nematic phase, we have near 100% Ising order. Okay, so then.
Before you move on, the temperature-dependent plot that you showed,
Yeah.
seemed to have some polarization above the transition.
Yeah, that's a pre-transitional. When we looked in the video, you could see these lines sort of starting so that their correlations grow in the nematic phase. So, so that's what's happening here. I mean, you have to put a field on to measure the polarization. You put a field on and you integrate the current. So, yeah, this is fairly common. Okay, so then at the same time, actually the same year as RM734 was made, a Japanese group reported DIO. Okay, so DIO is isotropic, a real nematic, an unidentified phase, and then this phase that they called ferroelectric-like. Okay, so this attracted our attention, and Dave made DIO. And so we looked at DIO. Okay, so the main question is this ferroelectric-like phase the same phase as we have in RM734? Okay, so the way to determine that is to make mixtures of these binary mixtures, and then look at the phase behavior across the phase diagram. And what you see is that the ferroelectric nematic, or this RM734 phase, stretches across the phase diagram. So it's the same phase. Now the interesting thing about this is that, this phase boundary is fairly straight. That with respect to the thermodynamics of the nematic and the ferroelectric nematic, this behaves like an ideal mixture, which means that in the mixture with respect to the ferroelectric nematic ordering, an RM734 molecule can't tell whether it's interacting with a DIO or with another RM734. Okay, so the molecules are behaving, very similarly in this phase. Okay, so having got to this point, it seemed to me that we weren't going to end up with just two molecules doing this, even though at this point in the history of liquid crystals, there were like 500,000 molecules that have been made, 500,000 nematic molecules. So a question was, why did it take so long to find this? But having found it, I was fairly certain that there were going to be more. So we coined this idea of a ferroelectric nematic realm with two molecules in two phases. So it wasn't much of a realm, but it was a good idea, because after 5 years of international work, now there are 500 molecules and 15 phases in the ferroelectric nematic realm. So this is a sort of a burgeoning area of liquid crystal science. Okay, so then the question is, what's special about these that somehow is lacking in the first 500,000? So I think the main features are here. So both of these molecules have terminal dipoles that point in the same direction and are very, very close to the ends of the molecule. So if you put this molecule end to end, then you get strong dipole-dipole interactions between these end groups. So that's a commonality. The second commonality is that in the interior, there's not sort of contravailing dipoles in the interior of the molecule. So if you look at RM734, you basically have a charge density wave between the two ends. You have two dipoles and a charge density wave. So the third feature are what we call sticky paws. So we have 3 Fs, each enabling, possible, target for these dipole-dipole interactions. We have 7 H's. This end group is very flexible, so it can sort of bend around to get into sort of interactions with this end of a neighboring molecule. And we have the same situation here, 3 H's and 2 oxygens. And then this general, the dipoles and no contravailing dipoles give you some net charge transfer from one end of the molecule to the other. So this end is negatively charged and this end is positively charged. So you have some direct charge interactions in a sort of end-to-end assembly. Okay, so we looked at this in detail in the atomistic simulations. So here's the molecule. We pick a molecule, and when we assign it a coordinate system where the z-axis is along connects the 2 ends. The origin is around here. So we then calculate the charge density of this of the chosen molecule and of all the other molecules and average over the ensemble. So these plots show the charge density, conditional charge density of the chosen molecule, and then the conditional charge density of all the other molecules out here, and then the chosen molecule in the middle here. Okay, so we can look at we have a sort of blow up of the ends, but in the middle you see this charge density wave. So amazingly, you see this also a charge density wave, in the above and below here. Okay, so this is a conical structure. These are spherical caps of charge, and basically these charge density waves match the charge density wave in the given molecule when it's sort of in a position of sort of being in this end-to-end association. So these structures are coming from molecules that are tethered, that essentially, the tethered molecules dominate, this volume, this conical volume. So we have association that enables the molecules to be, they're not confined to be in a certain orientation. They can be sort of spread out over a broad range of angles. This shows sort of these bands matching the bands of the molecule. So this is the region around the end, the tethering point. So this is a fixed nitroxy, the 2 oxygens, and the methoxy groups of the tethered molecules sort of rolling around, sliding around. This is the van der Waals surface, sliding around, strongly attached to the, to this nitro. And then here's the other end of the molecule where you have the methoxys, occupying a large volume because they're so flexible, and then the nitros attaching. So this attachment's like 2 magnetic ball bearings rolling around on each other. Okay, so this shows the role of this multifunctionality. So these are snapshots of tethered pairs, and you can see that the methyl group is like a little radar antenna. So it's always sort of looking around or following the the nitroxy around. So this is the role of this flexibility. Okay, so looking at the sort of the numbers of molecules that are in these cones, it seems like we're definitely over what would be a percolation threshold in a network. So we have the central molecule, sort of, in this case, sort of interacting with two molecules in the next layer, et cetera, et cetera. So above a percolation threshold, that depends on the details of the network, you have the appearance of an infinite cluster, which is essentially a phase transition to a state which has a growing, as you increase the probability, a growing number of oriented, sort of chained molecules. So seems to us that this is the basic mechanism for the ferroelectricity, which you can also see in like an Ising kind of model if you add terms that correspond to this sort of flexibility in terms of a given molecule has a choice of numerous sites to which to bond to. Okay, so then we started out with these two phases, the ferroelectric nematic, and then this extra phase that's in Dio. Okay, so we either discovered or structurally characterized like the first 6 phases of the ferroelectric nematic realm. And so you can take the ferroelectric nematic and add chiral dopant. So this induces the director to spontaneously form a helix. So this is like a chiral nematic, ferroelectric nematic. So CB15 is the chiral dopant. It has a carbon. This tetrahedral carbon has something different on its 4 branches. So this is a molecule. This molecule is not superimposable on its mirror image. So that chirality, that handedness, is expressed in the macroscopic structure of this phase. Okay, so then there are molecules where these molecules all tilt up. And so a heliconical ferroelectric nematic, where the molecules are basically rotating on a cone. And this can be induced by adding chiral dopant, or there are phases where this happens spontaneously. So you go from a uniform ferroelectric nematic phase transition to a structure like this, which can be either left-handed or right-handed. And the left-handed, so then macroscopically you get a phase separation. You have domains where you have left-handed heliconical and right-handed heliconical.
Is that angle varying continuously from 90 degrees as you cool into that phase, or it's a first-order transition?
I think you could have both. I think they're both. But this pitch can be macroscopic, so you can get optical diffraction, effects from it. Okay, so then this extra phase in Dio is actually a lamellar phase. So you imagine in 3 dimensions sheets. So this is a stacking of sheets. In this sheet, the polarization is up, and in the neighboring sheet, the polarization's down. So this is an antiferroelectric phase. So you have domain walls here where the polarization, it's pointing up, and then there's a nematic layer nanometers thick and then pointing down. Okay, that's the smectic ZA phase. There's a ferroelectric smectic A phase. So you have ferroelectric nematic, you cool the phase, you cool this, and the molecules sort of shift up and down and sort of get next to each other and form layers, okay? So here the molecules are normal to the layers, so that's a smectic A. Here the molecules are laying down parallel to the layers, so that's a smectic Z. So this is a ferroelectric smectic A. Okay, so then in DO, you start in the nematic phase. It goes into this. Then it goes into the ferroelectric nematic. Nematic, this phase, ferroelectric nematic. Okay, so then there are molecules where it goes nematic into this phase, into the ferroelectric nematic, and then into the ferroelectric smectic A. And then there are molecules where it goes directly from this smectic A into the ferroelectric smectic A. So you have this phase and you're cooling it, and then in each of these sheets you start getting sort of tenuous layers forming. And associated with that, this periodicity starts growing, so they kind of spread out, and this layering becomes stronger. So then you end up with this, macroscopic domains where here it's up, in the neighboring domain it would be down. Okay, and then there are another new phase is where you have this, and layers just form. So you end up with two sets of layers, a set of layers, horizontal layers, and then this set of vertical layers in the same phase. Okay, so then you can imagine combining this smectic A with twist. So what happens if you put chiral doping in the smectic A phase? Well, so if you want to twist this, you can imagine it's horizontal twist axis where the director is going like this, okay? But then that twists the layers. The layers don't like to be twisted. So then what happens is that you get a twist grain boundary phase. So the director will twist, the layers will fracture, and then you get these layers of screw dislocations which enable the layers to change orientation. So this transition to this TGB phase is formally analogous to the application of this twisting is analogous to applying a magnetic field to a type 2 superconductor. Okay, so then I would say unexpected of these new phases, which we found is this reentrant isotropic phase. So RM734, we add a small amount of this ionic liquid dopant. So these are organic ions that form a liquid phase at room temperature. So a tiny amount of this stuff creates a kinetic pathway to go to this phase. So we're cooling, transition starts, these black spots appear, and then we end up with the whole sample being black. So between cross-polar and in transmission between cross-polar and analyzer, so this is an indication that it's optically isotropic. And then we found, once we learned this, we found a way of doing this without using the ionic liquid. All right, so in the context of the realm, the question is, what happens in Dio? Okay, and Dio does the same thing. So it's not it's not a kind of a freaky thing that RM734 does, but it's a property of molecules of the realm. All right, so this generally indicates that that this highly ordered phase has some kind of frustration, and it wants to do something that it can't do in the nematic, but it can do in the isotropic. So we don't know the details of this at this point. This.
Say how sensitive is it to that dopant? Like, what kind of dopant?
Well, as you add this stuff, then eventually, I mean, it makes the ferroelectric nematic phase go away. Eventually, you end up without.
But what I mean is, how specific is the chiral ionic dopant have to be? Like, can it be some other molecule? Or?
Well, there's a bunch. Yeah, we tried several of these ionic liquids.
They all do that.
They do the same thing. This is the garden variety ionic liquid. All right, so this is a dumbbell-shaped molecule. It has big globs of hydrocarbon at the end. So this stuff makes like nematic and smectic phases. But then, if you want to pack, you go to lower temperature. If you want to pack these, then you have to twist when you're packing dumbbells. Okay, so then that builds up domains which are twisted, and these domains organize into cubic phases, which are isotropic. So I think that this isotropic phase showing up is something like this. And then there's a defect phase, which is a birefringent. It's something like this, only doesn't have cubic symmetry, but it's birefringent.
Are these the same as the blue phase?
No. Well, the blue phase is sort of related, right, to this. All right, so now we'll turn to some phenomenology. So the main sort of physical difference between the ferroelectric nematic and the nematic is the addition of this electrostatic the space charge interactions. So if you have a divergence of the polarization, you have space charge. And then the space charge interact by this long-range Coulomb potential. Okay, so you can sort of see the effects of this if you just consider a one-dimensional reorientation in this, in the director field. So this angle is a function of z, and so these are fills three-dimensional space with basically sheets of polarization are in the same orientation. So if you just had the typical kind of liquid crystal elasticity, it just costs energy to produce a reorientation, a gradient in the orientation. So would just want this gradient to get smaller and smaller. So this, if you made this kind of deformation, it would just spread out basically to infinity. Okay, in the ferroelectric case, you have polarization splay, so that produces the opposite sign of space charge. So these charged sheets attract each other. So now this wall has an equilibrium width, which is this constant lambda. So this is a trade-off between Frank and polarization charge elasticity. So this length is square root of epsilon k over p squared. So the larger p is, the tighter this wall will end up. All right, so in in RM734, if you calculate this lambda, it comes out to something like 10 nanometers, which means that the polarization charge interactions are, overwhelm the typical Frank elasticity until the director is squeezed down to this very tiny dimension. Okay, so the sort of understanding the ferroelectric pneumatic textures is basically, trying to understand how nature is gaming you by finding new ways to escape polarization charge. Okay, so one way to escape polarization charge is going around in circles. Okay, so if you have bend defects, you have div p equal to 0. On the other hand, splay defects will have, space charge. Okay, then space charge also, this is the bulk space charge term, but then there's also a surface, there's a surface polarization, P dot, the normal to a surface, where the polarization ends. Okay, so we can get some appreciation for how big the polarization is in these materials. So if you have a slab of ferroelectric pneumatics, say surrounded by air, and it has a polarization, and then by some external means, you rotate this polarization 90 degrees. Okay, then you have polarization space charge on the surfaces, polarization surface charge. Okay, so then you're going to get an electric field that actually opposes this reorientation. So in RM734, this field is 6,000 volts per micron. So you'd have to put an external field. If you have a 1 micron thick slab, you have to put an external field of 6,000 volts to reorient the polarization. Okay, so you can ameliorate this situation by adding electrodes to your slab, so the red, and then shorting the electrodes. Okay, so then we have free charge running around to cancel this electric field. It'll be a complete cancellation if you can get the negative and positive charge in exactly the same plane. Then there will be no electric field anywhere, and you can rotate the polarization at will with no change in energy. Typically what happens though is you can't quite get these free charge and polarization charge in the same plane. So if you have, say, a gold electrode and you just put the ferroelectric pneumatic in contact with the electrode, then you still end up with a nanometer thick layer that's insulating. So you end up with a surface capacitance. So if you tilt over the polarization, then you'll have to do, you will have some electric field in the capacitors, and so that will cost you a little bit of energy, but nothing like in the bare case. So this means that if you actually apply a voltage across the electrodes, you can control the orientation of the polarization without ever having any electric field in the liquid crystal. You're only controlling the amount of polarization charge on the surface. So then the polarization will rotate more or less as a rigid block. So the polarization is rigid because any spatial variation will end up producing space charge. Okay, so another way of eliminating, so this is sort of tilting the polarization out of the plane. Now, if you have a slab, then there's the in-plane texture, and that's sort of free to do whatever it pleases. So you can get two-dimensional patterns where the where there's no space charge. For example, here we have a bend region and a planar region. So there's a boundary here. Boundary line is a focal conic, and these are walls where the normal component of the polarization is continuous, but the tangential component changes sign. So there's no polarization on the walls. And these walls should have this width lambda that I calculated before, but typically they're way broader. So this is the kind of questions that we're looking at, trying to understand, for example, what the structure of the walls in these parabolic textures. So this is a situation where you have a twisted cell. So the top of so this is a 10 micron thick, roughly, cell. On the top of the top plate, polarization's blue, and on the bottom it's red, and in between it makes a pi twist. So you have a one-handed twist and the opposite-handed twist. So if these two, if you have a vertical wall, then in the middle of the cell, these two yellow arrows end up pointing in toward each other. That's space charge. But if you have a horizontal wall, then they sort of pass each other by. So a domain between these these two textures will be extended to reduce reduce space charge. Well, so we have some cool experiments. Just you have a flat metal plate, you put a drop of liquid crystal, you stick a needle in it, and then you vibrate the needle. Okay, and then you have an electrical circuit that's the needle. Something to measure the current, the bias voltage, and the substrate, so that we are measuring the measuring the induced current, so just you get very nice, no linear response, a nice second harmonic response that depends on the bias voltage. I'll just get to the bottom line here because I wanted to get to the application part before time runs out. So what happens is when you put the needle in the vicinity of the needle, the ferroelectric nematic organizes into this sort of circular texture around, which you can control by applying a voltage. So you can change the angle of the polarization relative to the needle, and that enables you to tune this effect. Okay, so let's talk about two applications just to finish up. So we spun off this company, Polaris, to do electronic electro-optics. So if you have a ferroelectric nematic medium that's got a polarization, then if you apply an electric field along the polarization in one direction, the refractive index of the medium will increase. And if you apply it in the opposite direction, the refractive index of the medium will decrease. And it could be one way or the other, depending, relative to the polarization. But you'll always have this refractive index that's a linear function of applied field. So you can use this to do phase modulation. So you take the ferroelectric nematic, so we've done precision measurements of the amount of delta n you get for a given field. So that's a coefficient R33. Measuring this as a function of frequency in the sort of megahertz kind of range. Turns out that the materials that Polaris can make, these are chromophores doped into the ferroelectric nematic, have a R33 that's comparable to lithium niobate, which is the standard sort of solid state ferroelectric used to do phase modulation. But now recently they've been able to make chromophoric molecules that are also ferroelectric nematics. So you can have 100% sort of active medium in the the volume that you're using to do phase modulation. So the typical application is on a silicon optical silicon chip where you make a channel, a wave, which is a waveguide. You have infrared light going down the waveguide. You have ferroelectric pneumatic with the polarization transverse to the propagation direction, and then electrodes you can apply a magnetic field. Now the advantage of small molecules is that so we're not reorienting the molecules here, we're sloshing electrons back and forth in the chromophoric molecules. And in molecules, this is an extremely fast effect. And they've been sort of demonstrated this at 102 gigabits per second so far, hoping to get to the terahertz regime. Another application of nonlinear optics, ferroelectric nematic NLO, is that you can make a lot of interesting photonic devices with patterned films of liquid crystals. So if you pattern a radial pattern and shine light through this, you can generate this were linear polarized, it could be circularly polarized. You generate a vortex beam. If this is a ferroelectric nematic, then you can generate a second harmonic vortex beam. So you can do nonlinear optics, and so it's the liquid crystal makes a nonlinear optical medium that can be sort of spatially patterned. Another application that's been demonstrated is to generating entangled photon pairs using the ferroelectric nematic as a bulk second harmonic medium. So this is, a la Zeilinger. Okay, so with that, I'll finish. Thank you.
Thanks, Noel. We have time for some questions.
Yeah. So all the molecules you were talking about were rod-shaped molecules. Is there any prognosis for discotic version of ferroelectric materials?
Yeah, you can make cone-shaped or, kind of flat molecules that have, some kind of polar thing sticking out. So they're in the literature.
Of the 500, it's already been discovered.
Yeah, I mean of the 500,000, 99.999% of them are just rods, but there are these other ones.
I have a question about the phase transition between nematic and ferroelectric nematic. During the phase transition, will these liquid crystal molecules rotate by pi degree, and will they expansion of the volume, or they just move to different positions?
Well, I think, yeah, I mean, they have to reorient. That's the only way you can change things, right? So on some scale, they're reorienting.
This will cause volume expansion.
Well, yeah, I mean, in the nematic, as you approach the phase transition, these, the polar correlations grow, and they grow along the director. They get, these end-to-end correlations are growing.
were looking at the ionic liquid enhanced conversion between your different phases, and you say that you tried a number of, I mean, the lovely thing about ionic liquids, of course, is that they're like a zillion, or it's combinatorially large set of molecules. And you said you explored probably the cationic dependence of that, but did you explore the anionic dependence of that?
Yeah, I think we looked at, let's see, what EMI, we looked at EMIM.
Yeah, right. So EMIM and BMIM, that's the standard thing, is to look at how the aliphatic group on the cation influences things. But there's a whole other realm, to use your word, by exploring the anionic spaces.
Yeah, I'm not sure what exactly the other ones were.
Yeah.
See, what was I going to say? Forgot, sorry.
Anyway, thank you. It's worth doing.
Maybe I'll ask.
Oh, I say we, by sort of the thermal cycling in the right way, we could get this isotropic phase, without the ionic liquid. But on the other hand, not to take anything away from Dave, but you make these molecules, you purify them, but they're not pure at the 0.2% kind of level. So the undoped RM734, I mean, just getting this may be an impurity effect under any, under any circumstances. We don't really know.